Okay, so to round off today's session, we have Leeat Yariv, who will talk about dominant solvability in random games. Over to you, Leeat.
Thank you. Thank you very much, Mihai, and thank you very much, Marina and Naveen, for organizing this great conference. It's also really nice to see friends from far away and nearby virtually, so thank you all for being here. All right, so this project is jointly written with my colleague Noga Alon and our stellar student, Kirill Rudolph. Kirill is actually on this call, so he'll be manning the chat and able to answer any questions that come up. All right, so a game is strict dominance solvable if the iterated elimination of strictly dominated strategies generates a unique Nash equilibrium. And in this paper, we're focusing on pure strategy, strict dominance solvability, which is a fundamental concept that touches upon many, many applications. So you can think about voting, where it was actually first introduced, to auctions, to oligopolistic competition, to global games, and so on and so forth. Now, implementation in iteratively undominated strategies is quite appealing. It has some nice features. In particular, it's simple in the sense that the order of elimination doesn't really matter. In addition, it's only ordinal rankings of payoffs that really affect the outcome rather than cardinal payoffs. It's also robust in that both the designer and also the players that play the game don't need to hold precise beliefs about other agents. Nonetheless, experimentalists have actually noticed over the years that while there are all these nice features, the number of iterations may actually affect the likelihood of an equilibrium being played. So just to put some data on this problem, let me show you a figure that relies on data given to us generously by Drew Friedenberg and Annie Liang. So they ran 200 random 3x3 games on MTurk. And so on 3x3 games, if someone plays randomly, the probability of any action is 1/3. So that corresponds to this horizontal dashed line. And the first thing to note here is what appears on the rightmost column. So this is the probability of playing the equilibrium when the game is non-solvable, but there's a unique pure Nash equilibrium. This is much lower than what we see in these middle columns that correspond to dominant solvable games. So that's already comforting about dominant solvability truly being an appealing thing. Nonetheless, what you see on the leftmost column is the likelihood of play of an undominated action when some action is dominated. That's pretty close to 1, which is in line with our love for games that are solvable and dominant strategies. However, as we look at games here in these middle columns that are solvable and involve for a player either 1 or 2 iterations or 3 to 4 iterations, the more iteration a player needs to go through, the lower the likelihoods, both in terms of magnitude, but also significance, that they actually play equilibrium. So overall, our goal in this project is to characterize features of this iterative elimination procedure in general random games. So that's what I'll try to show you. And in particular, we're going to focus on 3 facets of game simplicity. So the first one is just how common are strict dominant solvable games. The second one will have to do with their complexity. So suppose a game is dominant solvable, how many iterations would we expect it to entail? And the last one pertains to games that are not dominant solvable necessarily. It might be the case that the process of iteration actually is effective in simplifying them and that it allows for a reduction in the number of strategies. So we'll want to know how many strategies survive even if the game is not solvable. So let me preview the results. Now, most of what I'll say, I'll tell you about today will focus on a very particular case of a 2x-n game. So 2 players and 1 player has 2 actions. We have much more general results extending both the number of players and the number of actions. I'll try to preview them briefly, but I know everyone is tired, so I'm just going to focus on this special case. So it probably doesn't come as a surprise that the probability of dominant solvability is pretty low, especially for larger games. And in fact, for 2x(n) games, it asymptotically vanishes at the rate of 1 over square root of n. And in fact, as you increase the number of actions of the first player, that rate becomes faster and faster. Now, in terms of how complex these games are, we have some slightly bad news in that even dominant solvable games seem to entail many iterations. So for example, in the 2x(n) case, the conditional number of iteration is asymptotically 3, which is the maximum possible one. And as you increase the number of actions of both players, the number of iterations required increases rapidly. This is a little bit alarming in view of some of the data that we have, because we know that in general, players have fairly limited ability to go through more than 2 or 3 iterations. Now, the last item that I want to tell you about is how complex.
Clarification, you're using the word probability. What's the distribution on the space of games? These are ordinal games. Uniform?
I will be very formal, but yes, we're going to look at random games, completely uniform. And at the very end, I'll tell you something about other distributions.
Fine.
And I'll be more formal in a minute. All right, and the last question pertains to how complex surviving games are. And what we'll show you is that there's a bit of a silver lining to our other 2 types of results. So for example, for 2x(n) games, and in fact, as long as one of the player's action sets is relatively small to the other one, the number of surviving actions is going to account for a limited fraction of the actions. In particular, for 2x(n) games, it's going to be distributed normally with a mean and variance that behave like log n, which means that the fraction is vanishing. It behaves like log n over n. And in fact, it's very simple to get there. You reach that in only 1 iteration asymptotically. So this will also qualitatively be the case when one of the agent's actions is of the order of log n and the other one is n. But if you let both action sets increase in volume, then there's nothing to eliminate very quickly. So if you think about games in which all the players have the same number of actions, this process of iteration doesn't get us very far. All right, so let me describe to you the setting more formally. So we're looking at non-cooperative, simultaneous move, one-shot, complete information game. That's a mouthful, but basically we're looking at your textbook normal form game. There are going to be 2 players in this talk, so we'll call them row and column, and a finite action set. So row will have actions 1 through n, and column will have actions 1 through n. And we're going to focus on pure strategy strict dominance, so that will allow us to focus only on ordinal payoff rankings. Now, this is kind of important, and let me show you kind of a link which will be useful in how we generate these games between ordinal payoff rankings and permutations. So think about this silly example where here we're looking at the payoff matrix of column. And clearly the middle action is dominated for column because it generates payoffs that are coordinate-wise lower than the third action. Now, what matters here is really just the ranking of payoffs. So everything that's in this matrix in terms of the iterated elimination process would be captured if we just wrote where is the highest payoff in each row and where is the middle payoff and where is the lowest payoff. In other words, we can capture everything that matters for the iterated elimination process as a permutation that corresponds to each row. So this is how we'll describe the payoffs. We'll basically randomly determine permutations. So let me tell you what I mean more formally. So denote by S sub n the set of all permutations of 1 through n. Then we're going to generate random payoff matrices for row, that's going to be R, and for column, that's going to be C. And for each action of column, rows payoffs, the corresponding columns, will be uniform on the set of permutations Sm. And for each action of row, columns payoff will be uniform over the set of permutations of her action, just as in the example that I just showed you. And what we're assuming is that we have this random selection of columns and rows for our players, which are mutually independent. So going back to Pradeep's question, this is basically a uniform random distribution over the ordinal characteristics of the game. All right, now it's important to note, if you want to keep an example in mind, you could think about just determining each entry of the game matrix uniformly from 0, 1, or normally, or whichever distribution you want. You could even use different distributions for different rows of column, for example. In that sense, this way of writing it is payoff distribution free. But ultimately, what we'll be interested in is this random game, G of Mn, which we'll focus on for most of the talk. So this slide basically captures the entire model that I'll talk about today. Now, there will be these 3 facets, and I'll remind them to you as I go along. So I'm going to introduce annotation, but I know it's late in the day, so I don't expect you to remember. But just to kind of embed it, we're going to focus on the probability of strict dominant solvability. So this is going to be this pi of Mn. Then we're going to think about the conditional number of iteration, conditional on dominant solvability. This will be I of Mn. And then we'll want to understand how complex are surviving games, regardless of whether they're dominant solvable. So we will want to know the number of surviving actions, S for surviving, whether superscript of R for row or C for column. And sometimes we'll also be interested in the number of undominated actions in the first iterations, which will be denoted by U, either with a superscript of R for row or C for column. And that's kind of interesting because whenever they're singletons, we have a game that is solvable in dominant strategies. And those are pretty popular in our literature. All right, so here's what I'll do to you in the next 30 minutes or so. So I'll mostly cover these main results for 2 players, and in fact, I'll even restrict attentions for 2 actions for one of the players, just to show you some of the techniques that we're using. And throughout, I'll try to tell you what we see for larger games, just so you have a sense of the general results. At the end, I hope to have a few minutes to tell you what happens with alternative distributional assumptions. So we are well aware that most of the games studied in the literature are not random. So we try to look at various other games, constant sum, potential games, games of strategic complements, and so on. And I'll try to show you a tidbit at the very end, and then we'll be done. All right, so let's start with dominant solvability, and we'll start with the role player when the role player has only 2 actions. So we're considering here a payoff matrix for row that looks like this. Now, the probability that row has 1 undominated action is exactly the probability that she has precisely 1 dominant row. 1 dominant action. Or in other words, it's the probability that, for example, the top row dominates the second row. So this means that coordinate-wise, the first row is larger than the second row. And since each coordinate is larger with probability 1/2, this occurs overall with a probability of 1/2 to the end. And similarly, we can also have that the bottom row dominates the top row. That will occur with the same probability of 1/2 to the end. So overall, the probability that row has precisely 1 undominated action is vanishing at an exponential speed. It's going to be highly unlikely as n grows large, and it looks like 1/2 to the n-1. Now for column, it's going to be slightly more intricate. So the first thing to note is that we don't really care about the labels of actions for column. All we're going to care about is how many are undominated. We don't care about their names. So without loss of generality, we can fix the permutation that defines the first row for a column as just the identity permutation. So we'll just assume that the payoffs are strictly increasing in the first row that corresponds to column, right? So then we'll have these n factorial possible permutations for the bottom row. Now, the first thing to note is that we can already calculate the expectation of the undominated actions. And the way to do this, because of linearity of expectations, is basically to just sum up the probability that each action is undominated. So notice that the rightmost action, because we have the highest number in the top row, that's for sure undominated, right? So that happens, it's undominated with probability 1. Now, the action right to the left of it is going to be undominated if and only if C2n minus 1, this element, is greater than C2n. That again happens with probability 1/2. In fact, we can continue in this way till we get to the very left. Here, this action is going to be undominated only if C2 is greater than everything to the right. Or in other words, if C2 equals to n. And that happens with probability of 1/n. So overall, what we see already, and you see kind of the hints of this log n that I suggested in the beginning, is that the expected number of undominated actions is going to be the harmonic sum of order n, and that asymptotically behaves like log n. So asymptotically, we're going to have a vanishing number of actions that are undominated. Okay, but we want to know their distribution. So let me show you how that's constructed. So let's denote by f and k the number of possible permutations of that row, again, out of n factorial possible permutation that correspond to precisely k strictly undominated actions. So now I'm going to show you how we construct a recursive formula for f and k, which will be at the heart of all the calculations also, I'll show you. So there are two relevant cases to consider. The first one is when C21 here is less than n. If C21 is less than n, this means that action 1 is dominated. So if we're looking for k undominated actions in this entire game, we'll need to find k undominated actions in the remaining 2 by n minus 1 game. Now, there are n-1 options for C21 to be lower than n. So this contributes to our calculation, this term here, n-1 times f of n-1, that corresponds to the restricted game, and we'll have to find k undominated actions there. Now, if C21 equals to n, then action 1 is undominated, and we'll need to find only k-1 undominated actions in the remaining game. Now, there's only one way in which C21 equals to n, so now we just have an addition of this term. Okay, so we found a recursive formula for f and k. Now, as it turns out, this corresponds to something that combinatorics folks call the unsigned Stirling numbers of the first kind. So this is just precisely the same recursive formula that I just showed you. So what we have is the following lemma from all this discussion. So for any n, we know precisely the probability that row has exactly one undominated action. That's just 1/2 to the n-1. And for any k, the probability that column has precisely k undominated actions is just the Stirling number that comes from this recursive formula over n factorial, all the possible permutations of the second row. All right, so as a little mental break, the history of these numbers is kind of curious. And in fact, it seems likely that they are misattributed to Stirling. So it seems like Thomas Harriot, this handsome dude on the right here, who was a British mathematician in the 1600s, actually came up with it around 1600. It was named in honor of James Stirling, who lived almost a century later, between 1692 and 1770, by Niels Nielsen only in 1904. And interestingly, a lot of the characteristics of these numbers have garnered a lot of attention in the last few decades, and we're using some results from the 1990s. I'll allude to one if I have time at the very end. Now, these numbers have various interpretations. So in combinatorics, for those of you who are kind of into permutation stuff, C and K actually enumerates various constructs, including the number of permutations of n items with exactly k cycles. From an algebraic perspective, these numbers actually are very useful numbers, as it turns out, because they're the coefficients in the expansion of the rising factorial. So the rising factorial is this polynomial xn, which is just the multiplication of x by x plus 1, etc., till x plus n minus 1, and they're just the corresponding coefficients. And that's actually useful in some of our calculations. All right, so now I'll describe to you the ultimate result on the precise probability of dominant solvability. And for that, I'll need a tiny bit of notation, and I hope you'll forgive me. So the double factorial of a number is just defined just like a factorial, only the multipliers have the same parity. So for example, if you have 2n minus 1, this is an odd number. So we just multiply all of the odd numbers up to 2n minus 1. And 2n double factorial is just all the even numbers up to 2n, their multiplication. And the Wallace ratio is the ratio of two double factorials. And as it turns out, it can also be described as the ratio of gamma functions, where, just to remind you, gamma of 1/2 is the square root of pi. So now we can finally completely describe the probability of dominant solvability. So the probability of dominant solvability is 2 times the Wallace ratio. So you can write it as this formula. It's strictly decreasing in n, and asymptotically, it behaves like 1 over square root of n. In fact, with the proportional ratio of 2 over square root of pi. So let me show it to you and give you a little bit of intuition, and then I'll show you some pictures. So how do we even calculate this thing? Well, I already showed you how to calculate the distribution of the number of actions that survive for column, right? So these are all the options for column. Now, when we think of whether the game is solvable, certainly if column has only one action remaining in the first iteration, then it's dominant solvable. Now, if column has only precisely 2 actions remaining, then row is now facing effectively a game that is 2 by 2. And the probability that it's dominant solvable is going to be 1/2, or in other words, the probability that row will be able to eliminate something. And in fact, when column has precisely k remaining actions after the first round, the probability that row will be able to do anything from our calculation is 1 over 2 to the k minus 1. So essentially what we need to do is sum up all of these orange paths that lead to the word yes. And the rest is algebra. All right, so let me show you some pictures. So this is what you see here in the blue line is the probability of dominant solvability as we increase the number of actions of column. Superimposed on it is the asymptotic approximation. And what you see is that the asymptotic approximation is actually a pretty good approximation, even for very small n. And the probability declines pretty quickly. Now, just to allude to larger games, as you increase the number of actions of the row players, you see, again, a decay to 0, and it's more and more rapid. All right, now I'd like to tell you something about the conditional number of iterations. So the first thing to note is that if you have exactly 1 iteration conditional unsolvability, that basically means that both row and column have strictly dominant actions, right? These are games that we really love. These are the games that are strictly dominant solvable. Now, the probability of that is just multiplying the probability that each of them has a strictly dominant strategy. And we're dividing here by the probability of dominant solvability just because we're looking at the conditional. And if you do the math, asymptotically, this goes down to 0 very fast, in fact, exponentially. Right? So these games that are solvable with strictly dominant strategies, they're a rare animal. Now, similarly, we can also calculate in much the same fashion, I won't go through the algebra, the probability that you need precisely 2 iterations, that also goes to 0, but a bit slower, or the probability that you need 3 iterations, which approaches 1 naturally, because the others approach 0. So what we have ultimately is that the expectation is strictly increasing. In fact, it's increasing at the same rate to the maximal possible 3 at a rate of 1 over square root of n. So this is a little bit alarming, and I already mentioned it in the beginning, because these are, in principle, some of the simpler games that we're looking at. And we know from various data sources, particularly experimental, that players often have a fairly hard time doing more than 2 or 3 iterations. And here, even in these games, we reach 3 pretty quickly. And just to show you a figure, this is what it looks like. Again, we're superimposing the precise calculation of the expected number of iterations with its asymptotic approximation, which are very close very quickly. And what you also see is that as we increase the number of actions of rho, this number of iteration increases as well. And in fact, when both players have the same number of actions, it increases pretty rapidly. So let me connect it a little bit to virtual implementation. So this is a beautiful paper by Brook and Matsushima from 1992 that suggested that a large class of implementation problems can be approximated by dominant solvable mechanisms. So in some sense, this result makes, our observations make this result even more remarkable than it seemed originally, because dominant solvability is so rare. In some sense, it suggests sort of that the dominant solvable mechanisms are dense in the set of all mechanisms. So it's quite remarkable. On the other hand, it also warns us that there might be a vulnerability there, in the sense that we may need a lot of iterations in these mechanisms that are used for approximation. And I think it might be useful to think about how to characterize simple mechanisms. And we're not the first to suggest that. So even Hitoshi Matsushima has a short sequence of papers that thought about implementing stuff in very few iterations. And I'll give a shout out to Naveen, who has a very lovely paper that looks at the implementation in 2 stages when agents have a small preference for honesty. So I think this is something that is a really fascinating topic to think about. All right, so the last aspect that I'd like to tell you about is the number of surviving actions. So first of all, for the row, she has exactly 1 surviving action if and only if the game is dominant solvable. So if she can cancel one of her actions, we're done, because column will just pick the optimizing action for her, and that will be it. So therefore, the probability that the surviving action is 1 is going to be just the probability that the game is dominant solvable. That's going to go to 0 very quickly. And in fact, the resulting expectation of the number of surviving strategies for row is going to be just 2 minus this probability, which again is going to converge to 2 very quickly. All right, how about column? How do we calculate this? So I'll give a bit of an intuition of how we calculate this. You can zone out if you don't want to hear the details. I'll show you the result in a minute. So this is precisely the tree that I just showed you before. So because we're looking at strict elimination, the order of elimination doesn't matter. We look first at the column, and we have the precise distribution of all their undominated actions. And then there are 2 options in every node. So first of all, if she has precisely 1 undominated action, that's it. That's the surviving action. Now, if she has 2 surviving actions after the first stage, either row can eliminate something, in which case we have a dominant solvable game, and ultimately the surviving actions of column will be exactly 1, or not, then she'll remain with 2. In fact, that's true for general K. Either row can eliminate something in the second stage, in which case the game is dominant solvable and column has precisely 1 dominant action, or row can't do anything and we're stuck with K for the column. So basically what we need to look at is the resulting distribution. And you can already see from here that you would expect a spike at 1, because 1 is kind of special here. All right, so here's the proposition. So as it turns out, column's number of surviving actions is asymptotically normal. And in fact, I know this is kind of a heavy proposition. What you should really focus on is what's in orange here. So the expected number of surviving actions, as well as the variance of surviving actions, behaves like log n. So that's really a silver lining to our results, because it suggests a very small fraction of surviving actions for column. Furthermore, because the expectation exactly coincides with the expectation we started out with of the undominated actions, it suggests that we're getting everything in one iteration. So we're simplifying the game dramatically and in only one iteration. So that's kind of good news. And this result actually relies on some fairly frontier stuff in combinatorics. In particular, it's inspired by a beautiful paper by Huang in '98. All right, so let me show you some pictures. So these are the expected number of surviving strategies. Again, following our convention from before for our 2 by n games and the asymptotic approximation for them. And you see that, as we increase the number of actions here, you see that the fraction converges to 0. In fact, that's true as long as the number of actions of the role players is relatively small relative to the column player. Now, this is just to give you a sense of the distribution. So we fixed here the number of columns actions to be 50, and I'm just showing you the resulting distribution of surviving actions for a different number of actions per row. And what you see is that it looks like a normal pretty quickly. And in fact, here for n equals to 50, we see this spike at 1, which I alluded to when I described the tree, if you focused on this. Now, when the number of actions of row increases together, so for example, just keep in mind the case in which both players have the same number of actions, then there's nothing to do. So the game doesn't get simplified at all very quickly. So you see here that even when we look at n equals to 5, it basically grows linearly, nothing is eliminated. The process of iteration doesn't get us very far. All right, so in the last few minutes, I'd like to tell you about alternative distributional assumptions. So certainly games that we study in the literature are not random. They have very particular features. There are reasons that make them interesting. And one may be concerned, and I think Pradeep raised it right at the outset, of whether the results are driven by the fact that we're assuming here a uniform distribution over games. And to us, of course, in order to get analytical results, we need to make some assumptions, but I'll show you briefly some results from experiments and from simulations that suggest that perhaps the results are not terribly special to this random structure that we imposed. So the first thing I'll show you comes from lab and random games. And again, this is from data that was generously shared with us by Drew Fudenberg and Annie Liang. So they ran 200 random 3x3 games to study initial play. They basically emulated exactly our games, but each payoff entry was uniform from a discrete set of payoffs. So they didn't rule out indifferences. So that's the only difference from the way we randomly determine payoffs. They also had data from 86 lab symmetric 3x3 games, which came from 6 different lab experiments collected by Leighton, Brown, and Wright. So I'll show you some features of these games. So the first thing to note is that if anything, the random games that we're studying are quote unquote strategically simpler than these games that the literature is focused on experimentally. And that's true in terms of both the number of pure Nash equilibria and the number of surviving actions. So what you see here in the orange left bars are the games that correspond to our random games. And the dashed lines correspond to Freudenberg and Leand random games, and the white blocks correspond to these 6 various experiments and 3x3 symmetric games. And we see far fewer pure Nash equilibria, and we also see fewer number of surviving actions. So in many ways, our games are simpler. Now, we might look at it more generally by focusing attention on random games that have very particular features that our literature focuses on. So we focused on these, and now I'll tell you everything for balanced games where both players have the same number of actions, just so that I can also focus on symmetric games, but you could also think about imbalanced games. So what we're looking at is this G of NN. You could also think about generating games that are symmetric. So we could do everything that I told you about with symmetric games. You could also think about potential games where there is an ordinal potential to the payoff matrix. Constant sum games, in particular zero-sum games. Games with strategic complements. In other words, games in which there are non-decreasing best response functions for both players. And we can think about both just standard strategic complement games and symmetric strategic complements games. So I'll now show you a bunch of figures for all of these games, just to give you a sense of where our games stand relative to all these classes of games. And last, there is also the lab games that I already mentioned. Okay, so here are the graphs that correspond to the probability of dominant solvability. In the red solid line, you see the graph that corresponds to our random games. This is what I've been talking about. Now, interestingly, practically all of the games that I mentioned, all of the classes of games, other than this particular one, which I'll get to in a second, generate an even lower probability of dominant solvability. In fact, the lab games are really below. Even the strategic complements games that are actually seem to suggest a more positive image of the probability of dominant solvability converge to 0 very quickly. So by the time you get to an 8x8 game, this probability hovers around 2%. Now, if you look at the number of iterations, our games are a little bit more complicated than these other classes of games. Nonetheless, again, as long as there is significant probability of dominant solvability, so that's why we're restricting attention to n, which is smaller than 8 here, the number of iterations required is basically above 2 for all of these classes of games. So these games become complicated from a practical perspective pretty quickly across the board, across these different varieties. And the last thing is the number of strategies that survive iterated elimination, whether or not the game is solvable. And as it turns out, we see very similar figures that correspond to these different classes of games. And all of them seem to increase almost linearly as you go beyond n equals to 5 or so. All right, so I'll conclude. So there are essentially these 3 facets of complexity that I tried to show you. So I tried to show you that getting dominant solvability, that's probably in line with common wisdom, is pretty difficult, and we can even quantify the speed. Dominant solvable games are fairly complex in that they require many iterations. Iterated elimination, nonetheless, greatly simplifies the game. That's where the silver lining comes in, at least when one action set is relatively small. And in fact, it's done in 1 iteration. So that's a truly nice thing. Now, more players I didn't really tell you about, but all the qualitative results hold. And the main qualitative results are robust to alternative distributional assumptions, as we discussed at the very end. That's all, folks.
Any questions?
Well, I have have a stupid question. Leeat, a natural, you took uniform over ordinal. One could look at the analog of uniform cardinal, where each entry for payoff entry of each player is uniformly from 0 to 1, which may, it may not lead to pretty mathematics, but it also seems to be a classical case.
It would be exactly the same. It would be exactly the same. So nothing would change. All that matters, as long as the distributions are IID, everything will follow in exactly this. So no result.
I see. So I'm missing something. The formula.
Because
IID and non-atomic.
Yes.
That's
right.
Okay. That's right. Yeah. So once you have atoms, you'll need to think a little bit about indifferences, and that would be annoying. But
but you could also think about domination by mixed strategies if you take.
That's harder. That's right. So that you would need cardinal payoffs for, and that's harder, and we don't know how to handle that. I should say that a lot of the applications of dominant solvability do assume pure actions, and arguably it's a simpler thing, but it's also simpler for us to analyze.
Okay.
Leeat,
Yes.
Two things. So one is actually, there's a question on the Q&A. Let me do that first before I had a question of my own. But so the question in the Q&A from Sam Gansfried or Fried says, is there a solution concept weaker than domination but stronger than Nash equilibrium that might be useful for games with similar number of actions for each player?
I don't know, useful in what sense? So I think, so our view is, at least my view of, with my experimental hat, is that we know that people have a hard time iterating more than 2 or 3 times. And so it's an interesting theoretical question of what you can implement with simple mechanism of this sort. And Naveen, you actually have a very nice paper that sort of does that under some assumptions on preferences of individuals. But I don't know if I'm answering the question that was asked. I'm not sure I understand it.
Yeah, I'm not sure exactly what was meant. Maybe he or she will expand if they'd like. So my question was, I forget, I may have lost it, but when you extend it to more than 2 players, are you still sort of looking at, I was trying to connect this with rationalizability, and so the question was sort of, are you doing essentially correlated rationalizability or just doing deletion?
No, we're just looking at the same sort of thing where you have multiple actions, say P players, and you're just looking at the corresponding normal form game. Okay, so now you can look at if you have 3 players, for example, each one will have an action set. Now, clearly, if one of them has only 1 action, you're back to our setting. If one of them has 2 actions, then it's a little bit more complicated because now they need to satisfy something. And as it turns out, even when you look at 2x2x3 games, the probabilities and the number of iterations become quite large. So the probability becomes very low. And so here, this is actually corresponds to 3 actions for each player with 4 players. That's, it's a tiny, tiny probability. And I can show you a picture actually. So this is just the probability that corresponds to a game with 3 players where we're increasing only one of the players' action sets. So I'm not sure I'm answering your question. So it's not rationalizability. We're not dealing with rationalizability here. We're still dealing with iterated elimination of strictly dominated strategies. We're just adding the number of players in the normal form game. I think it's not terribly surprising that dominant solvability becomes harder and the number of iterations goes up, right? I mean, it's natural that these games are more complicated. So in some sense, I think the surprise is that even some quote unquote seemingly simple games are complex. All right. Thank you very much.
Thank you, Leeat.